Okay, I guess we can continue. So, um, my plan is to start next on Thursday, the SVD stuff for like the tensors. I'm just going to finish telling you some more, like giving you some other examples where like this bracket notation is useful and finishing like saying a little bit about like the motivation for why I started talking about this in the first place, which was like this thing about the SVD and the probability and all that stuff. Um, so just kind of like to remind you some of like the stuff that I was mentioning last time. Um, so the idea is that so like the example I was mentioning was a qubit, right? Which is like the most basic example you could have. Okay, so the idea of a qubit is like, well, mathematically, the way we want to think about it is that it is represented as a vector, right? So it's represented by a vector. So again, like usually like the vector, you would just write it V. I'll just write it like this, which is like the Dirac notation for a vector. In fact, usually you wouldn't even put like the arrow on top of it. Just like the cat makes it clear that it's a vector. I'll just kind of like do a little bit of an overkill to emphasize that I'm just to remind you, I'm thinking about it as a vector, but I'm just putting these fancy decorations around it. Okay, and the idea of a qubit is that this vector is a vector in a two-dimensional vector space. So in a two-dimensional. Okay. And because it's in a two-dimensional vector space, we can write it as a linear combination of a basis, right? Like so, the usual basis you would it's called like this. It's related to this spin up and down thing that I mentioned before. So you can write it as a linear combination of the basis vectors. So this one is called the basis up, the spin up, and the other one is called the spin down. And we are assuming here that the these three vectors are of unit length. So V is of unit length, and the up and down states are of unit length as well. So V up and down are of unit length. And moreover, you can take the up and down states to be orthogonal. Okay, and moreover, orthogonal. So again, orthogonal just means that their dot product would be zero, right? But in this fancy notation, in the bracket notation, you can write that as in this way. So this is kind of like the orthogonality condition. Okay. And then, I mean, then at this point, you're just like, if you apply Pythagoras theorem, basically, right? Like, because this one has length one, and you're writing it in terms of like an orthonormal basis, right? Then by Pythagoras, basically. One would be C1 squared plus C2 squared. Okay. And it is that so these are two numbers that square to one, right? These are each non-negative, right? Because I mean C1 squared is not negative and C2 squared are not negative. So you have to, if you call P1 and P2 these two numbers, right? So you would call this one P1 and this one P2. So you have two non-negative numbers that square to one, and in like the usual interpretation of quantum mechanics is that those are interpreted as a probabilities that if you're trying to measure, spin up or spin down, that kind of like the state is found in one of those two possibilities. Um, it's called sometimes a projective measurement. or because kind of like the idea is like the state collapses into one of those two possibilities. But again, I'm just kind of not going to get into too much of that. It's just like motivation. So P1 and P2 are the probabilities of the state B being found uh, in it's being upward now. And then there's a more traditional notation which I might have gone which is like kind of like the notation in quantum computing, where like like you could call like the spin-off case like a zero, like a vector zero, like in the quantum computing term notation. You would write something like this. Oh, you have to be careful here, okay, because like if you put like a zero in a ket, so you're thinking about that as a vector, right? Not as the number zero, right? And that corresponds. I mean, like you can make like by assumption, like it is supposed to be basis vector, so you can just and since they were for normal, you can just assume that like this one is kind of like the canonical basis vector E1, so it would correspond to 1, 0. If you want to work in terms like entries or coordinates, you know. And then the spin down, for example, you could call it, the basic vector 1, and that would correspond to 0, 1. But then, that way you can kind of like certain operations that you do in classical computation, you can kind of like find kind of like I don't know, like rewrite them in this language and do like a kind of like a quantum version of them. So for example, just I'll maybe put some problems about that because it's a fun exercise to do that. But here's like an example of what I mean. So what is what would this be? So I think we got talked about a similar thing last time, which also remind you about the projection stuff. But it just like ignoring the like you have a cat, like for example, if you look at one of these pieces, you have a cat and a bra, right? A cat and a bra, and also you have here a cat and a bra. But we had talked about that this should kind of be maybe like a tensor product, right? Like that's something we had mentioned last time. So this would be some sort of like matrix, and this could be another matrix, right? You're just adding up matrices, and you would expect this to be a matrix, right? Um, Now you can kind of like, if you wanted, you can work in the representation in terms of entries, but it's kind of like useful to just kind of like think more abstractly. and now kind of like go to the entry representation of the graph and the test, and just like think about what it's doing to the specific basic vectors, like just like by like the properties. So for example, if you wanted to know what this does on the on on the vector 0, right? What would this be? So this would be, it is 0. Right? So it's going to be this applied to the vector 0, right? And then, well, the matrix is linear, right? Like, so that it is kind of like linear is like a product, right? So you can just do this way. Right? And this part corresponds to the inner product or the dot product between the state 1 and the state 0. Again, these now if you want to think about it in terms of their actual representations, they're just like orthogonal states, right? So this actually goes away, right? This one goes away because of like the orthogonality. Right? And then this is the dot product of the 0 vector with itself. I mean, that's just like the length where, if you think about it, so they are unit vectors, so this gives you 1, right? So that means that what the matrix does on the vector 0 is just send it to the vector 1, right? And it's kind of like this, you know, you can check it, that what it does on the vector 1, right? If you do the same for the vector 1, it sends it to 0, right? So so if you think about what it's doing, it's kind of like swapping the qubit 0 with the qubit 1. So it's kind of like a swap gate, or like a NOT, the NOT, right? Like, you know, takes like the in terms of Boolean algebra, you know, like the opposite, like the NOT, the proposition, right? So it is called like a swap matrix or the swap gate, right? So S is because it flips, like, you know, it flips the qubit, right? Since it flips 0 with 1. Or swaps, I guess, like that's why it's called the swap gate. And I'll put some of you know, I'll put as exercise. There's kind of like a thing, a version you can do for an and or an or. You can find kind of the analogs of what that should be in terms of like a matrix, like a matrix for representation. And has everyone heard about the Toffoli gate, the Toffoli operation? So that's like a reversible, you know, you can do a Toffoli thing. I'll mention, like, I'll put it in one of the examples, but all of, you know, the thing with the and, or like for example, an and is not reversible operation because it takes 2 bits and produces 1, right? So that's not a bijective function. But there's like a way to do all like the Boolean operations with like bijective operations, which is using like the Toffoli code. And so it's kind of like, I mean, it's kind of like a fun example to just rewrite it that way. So, you know, from that perspective, you know, if you have, all that I'm saying is that one of the reasons why you switch to this notation is because then it kind of just gives you some suggestions on how to try to transport certain stuff from this classical computation into quantum computation equation.
So instead of like computing this person, like we're like constructing like a tensor as we did for like dot products.
Right, right.
We can get if S is a tensor. What is it to our basis?
Right. Correct. I'm defining it just, I mean, I kind of like cheated, but you know, like I wanted to define a matrix, right? You can define a matrix by what it does in the basis, right? So I actually, you know, in my mind, I started with this, right? I wanted it to map the 0 cubic into 1 and 1 into 0. And from there, you kind of like go backwards and reconstruct the tensor, right? Or the matrix. And you can kind of like do the same for like the answer before. So you can start like, the thing is like that one, again, I'll put it on the, like, as an exercise, but, no, for example, let's use A for and, right? So you would want, the thing is like now you have to feed two weeks into it, right? Because and of two prepositions, right, or two Boolean operations. So like you would want the and of 0 and 0 to be 0. Like something is true only if both are true, right? So you would want the and of 1 and 1 to be 1, right? And then you would want the and of 0 and 1 to be 0, right? And the and of 1 and 0 to be 0 as well, right? And that once you specify that that's what you want to do, you can kind of think down completely what the operation should be, right? And you writing it in bracket notation is really fun because it is very clear just to read off what he's supposed to give you. Like that's like the bracket notation is kind of like the Leibniz notation in calculus. It's almost too good to be true. Like where like you can just get away with many things. It's like almost too dangerous, right? Like because like the Leibniz notation, that's kind of like the like the chair rule. The chair rule in the Leibniz notation like looks stupid, right? Because it just feels like, oh, you're just multiplying by the reduced, right? So it's almost you can kind of get away with things without knowing what you're doing, right? And the bracket notation is almost like that because it's almost too miraculous, right? So you kind of like can do like that's why and probably it would be fun to teach you like the course in linear algebra with bracket notation, but it may be too good to maybe not the best thing because then like there's certain things that you wouldn't even notice that you're doing because the notation is so too smooth. It is too smooth. You need some sort of more like issues like with the notation so that you just know what's going on. But it's very like fun too. Once you kind of get used to it, it is really fun, like very useful notation. Yeah, but I'll put some examples so that you find the and version, the whole like the control case, like the exclusive not. Well,
Some of.
so in this case, right, the swap gate, if you represented it as a matrix, right, it's a permutation. So this would be the matrix representation of the I mean, in terms of entries, right, you would find that you get these matrix. So yeah, this one does have like rank 2, but and I agree that the way I expressed it, it does feel like you would not be able to do it with just one factor, right? But I mean, with those arguments, you always have to be careful because how do you know that you could not have been clever and done it like So it's but once you write it in the matrix representation, you can kind of like see here like, oh, it does have like rank 2. So yeah, I agree with that. But yeah, like, the only thing is that in these like quantum circuits or like like quantum computations, like but the matrices have to be like orthogonal unitaries or like orthogonal, what they're called, like because they all of the quantum operations are reversible on the circle. So like that's why this complicated is useful to compare to like classical computing computation with quantum computation because complicated is like a reversible operation. But I'll put some examples. I'll put some problems about that because it's quite like the fun exercise to kind of get your hands dirty on the bracket notation. Just that reason. Um, okay, so yeah, I was just mentioning this kind of like to give you like a flavor of like how this works. The other thing I was saying, like what I was saying last time at the end of last time, is that if, for example, just going back to what I was saying last time, right? If you have the vector v, right, you can construct this matrix. I'll call it P sub v. Right, and what we were talking about is that would correspond to a projection matrix, right? That's what I was telling you last time. It squares to, it squares to itself, and it also happens to be symmetric. So that's, I mean, it the same. So therefore, like orthogonal projection. And geometrically, what that corresponds to is that if you have any vector, what does it do to any vector? If you have any vector, it just projects it onto the line, and just looks at the components, along the direction defined by vector v. So like what it does. I'll just do my picture pretending that it's all 3D, right? So if you had the vector v here, and you have the vector u here, right? Then the PV, maybe I should have, I'll make this one a bit shorter. Right, like the vector PV kind of like, I mean, there's kind of like a right triangle here, right? And so this one, this one would be this one would be right? Like that's like projects the vector u onto the line generated by the vector v. And you had asked me if there was the general formula, right? If you project onto vector space, right? So like I did post like the exercise over the weekend, so I don't know if anyone had like a chance to look at it. But if you had like you know, if you have more generally, right? If you have a vector space, here's like, let's say this is like a vector space. So this is a vector space or subspace, vector subspace of dimension R, right? And you have a vector U, right? If you wanted to find the projection onto that subspace, right? Let's say that this is supposed to be the projection of the vector U onto the subspace W, right? So again, there's secretly like a kind of like the idea is like this is an orthogonal projection, right? So this is kind of like a right triangle in the sense that this is complementary, so it's in the orthogonal complement. Then one elegant way to find like an explicit formula for the projection is that you find a basis for W, you do branch Schmidt, turn it into an orthonormal basis. So you would have like, I mean, this is going to be a terrible picture, but like hopefully you know what I'm trying to say. So you find a basis vectors W1, W2 up to WR, right? So W1, W2 up to WR are like an orthonormal basis of W. And then the formula for it's not too hard to convince yourself that the formula for the projection well I'll write like the actual projection matrix itself. It's just like a sum of tensor products, right? Like so it's kind of like it's just going to be oops. It's a kind of like a generalization of this one. So it's W1 plus W2 up to WR. So if you want like a more traditional notation, it would just be like the sum of the WI's tensor WI from I equals 1 to R, right? I call R because that would also be the rank of the projection matrix. So I did it on purpose to give it the name R, right? But rank is the dimension is R, but that also would match the rank of this projection matrix. And yes, sir.
So like, just to visualize, what would be the difference between PW and PW time? U.
Oh no, so PW, right. PW is the matrix itself, right? Right. PW of U is what it does to an actual vector, right? Right. So
PW is
this W is kind of like a subscript, right? Like I'm trying to. Yeah. Sorry about that.
is the matrix that includes
Right.
create.
Correct. It's the linear transformation. It's like it grabs a vector and it gives you the shadow of that vector. It's the operation itself.
Okay.
If you want to know what the output is, right? What is that shadow vector? Did you just apply like you just apply u to it, right? And for example, in the Dirac notation, in the Dirac notation, it would be wi with u. Right? But the idea is that these are just numbers, right? Like this is like the bra and a cat. When the bra and the cat meet, that is just a number. So if you want, you can kind of like write this number in front of the vector. So it's kind of like it has, just like it's a little bit of a way of rewriting it. Yes. I'll just put like the things that are scalars in black. Just to kind of like distinguish them from the actual vector part. Right. So it's a linear, it has to be a linear combination, like the shadow needs to be a linear combination, right? Like the shadow needs to be a linear combination of the basis vectors, right? So you have like the basis vectors here, and what are the coefficients of in front of the linear combination? They're like these, like WI.
Oh, it's basically doing branch splits.
I mean,
That also, we just basically took an inner product, like a dot product.
Right, right.
Between every basis vector and u.
well, that's the thing,
And
right?
then multiplied it by the basis vector itself and then added on.
Well, yeah, because the idea is like, that's why orthonormal bases are super useful, right? Because, you know,
Like basically the branch split is like the entire point of putting branch split was to find such basis, and then it was basically like this is one whether.
I mean, it is more or less. I mean, yeah. Once you have Gram Schmidt, there's almost nothing else to do. And why is Gram like? But right, like, what is the selling point of having like an orthonormal basis? That it's immediate to read off the coefficients, right? Like, so if you have, I mean, just like in general, if you have a vector v, right, it's a linear combination of a basis vectors which are orthonormal. Then how do you find these coefficient vectors? Not coefficient vectors, but just like the scalars, right? Like the coefficients in front of that make up the linear combination. You just dot it on both sides, right? You dot both sides of the equation with one of the basis vectors, right? But because this is orthonormal, this is one of these Kronecker deltas, right? This is a delta ij. It's only one when I equals j. So that kind of like collapses this sum into C sub j, right? And so that makes C sub j like the dot product of the two vectors. Yes.
So we give all the basis of our plane that we're projecting.
Right.
In this scenario, the plane is two-dimensional, but.
Right.
Why you put it up to the dot, okay, makes sense.
Yeah.
But what I'm trying to connect is how does like forming this giant tensor product of all the bases.
Mhm.
And then applying a vector anywhere outside or inside, right? It doesn't matter if it's.
Right. If the vector had happened to be inside, right?
Right.
It just gives you back that spits out the same vector, right? If you project that, if you apply the projection onto a vector that was already inside to begin with, it does nothing to you, right? So it just leaves it alone, right. But if the vector had been outside, which is kind of the interesting part, right? Then it just does give you the closest vector, the vector in the closest to it, yeah.
I'm just trying to think like how it does that. It just seems magical.
Well, the thing is that you just have to think about what it should do because you're saying, okay, kind of like the idea is okay, I don't know what this should be, right? But I just want it to be, I want this to be in a linear combination of the basis vectors, right?
Sure, yeah.
Right. So because it's supposed to be where's the eraser here? I think it's probably behind. So because this one should be a linear combination of the basis vectors, it has to be a sum, right, of the wi's, right?
Yeah.
So far, so good. And because this is an orthonormal basis, each of these coefficients can be found just by taking the dot product of these vectors with the basis, right? But I'll just use a regular notation. So far, so good. Okay, so the vector is supposed to be, the projection is going to be the shadow vector. It has to be a linear combination, has to be a linear combination of the basis vectors, right?
Yeah.
And because the basis is orthonormal, right? That's what the advantage of having an orthonormal basis, that each of these coefficients can just be computed as a dot product between the basis and the vector in question. That's what makes like the basis orthonormal.
There can be
Well, you just say dot. It's kind of what I was writing here, right? Like you just, if you take the dot product with one of the basis vectors, everything dies. Everything dies except that because they're orthogonal vectors. So like everything dies in the sum except like the same index.
if they're parallel.
Well, because they're mutually orthogonal except that, when
Except the same one.
except the same one.
The same one is the only one I work with too.
Right, and the same one because it's unit vector, if you do it with itself, it just gives you one. And then kind of like the idea of the projection being orthogonal is to say, well, because this projection is supposed to be orthogonal, I'll just assume that's how you find it. You just find it so that this vector has the same dot product. Is, as like what you would get just to replace it with you, because the idea is that, because this is like an orthogonal projection, if you think about the dot product in terms of like, the product of the lengths, like the cosine of the angle, these will have the same, the fact that this is orthogonal would tell you that like, you can just replace PW of u with u. That's kind of what makes it like, I mean, yeah, it takes probably I can tell you more about that. During numbers, but it's not too bad. It is like it is plausible once you think about what an orthogonal projection was supposed to be. Or another way to, if you want to think about it, okay, here's like an easier way, because u minus a projection, right, should be perpendicular to any vector here, right?
Yeah.
Okay, so that means that the dot product, this dot product should be zero, right?
Yes, yeah.
And that is the same as saying that u dot wi should be the same as u dot pw of u. Sorry, wi. You distribute the dot product. If you distribute this dot product, you get u dot wi minus pw u dot wi equals 0. And that tells you, that u and pw have the same dot product with each of the basic vectors. So u dot wi is equal to v w u dot wi. Is everything what that's done?
Yeah.
Yes, and then that's why it means, that's why it's called like an orthogonal projection, because that is what enforces that you can replace, with the dot product of projection. Just like the vector.
So you projected a vector
Mhm.
onto certain space.
Yes.
How do you project like tensor, any tensor
Uh-huh.
into the tensor space?
Well, I mean, there, like, it depends on what you want to do it, because, like.
Is that kind of what SVD does?
Well, it is, like, the FPV is not this, not per se a projection. Because the factors u and v, right, of the FPV, they're not projections, they're rotations, right? But if you want to, I mean, if you think of the tensor, I mean, once you have a notion of distance, right? In the tensors, there is an inner product between tensors, right? We talked about that. Once you have like an inner product, you can always do the projection. It's kind of like the same formula, but you just have to find a basis of tensors for the tensor subspace, and then you project, they are all Hilbert spaces. That's the name for it. Like a Hilbert space is just like a vector with a dot product. Whenever you have an a Hilbert space, you can kind of like do the projection more or less with this formula. It's just that instead of vectors, and the vectors are tensors, but it is really always the same. That's the same with Fourier analysis, right? If you have like or like the theory of orthogonal functions, right? If you have a function, right?
Like we treat it as if it's like
Right. If you treat it as if it's a vector, then you have like the I don't know, sine of x, cosine of x, right? What is the combination of sine and cosine which is closest to e to the x? You just use the dot product, senior product between functions, and then move down. So like once you have like the Hilbert space structure, that's how it's called. The formula is more or less always the same. Yeah. So
um just so I know, what class do we learn all the Hilbert spaces?
well, I kind of like it's drop breadcrumbs. It's like breadcrumbs things like on an undergraduate curriculum, but if you take functional analysis, that is where you do it kind of like in its full glory. I don't know, like, but as an undergraduate, I mean, in PDEs, I mean, like, kind of like as you go as you need it, right? So in PDEs, you would do a lot of it, or like a more mathematically oriented quantum mechanics course would go a lot over like if you open a quantum mechanics textbook, maybe chapter 1 or 2 will always be the mathematical aspects of Hilbert spaces because it's that's used like that's like the mathematics of quantum mechanics, like Hilbert spaces. So, uh, but yeah, like, but you will see it like from time to like as it's needed, like which is, but that's usually so you'll see it in many places, but maybe not kind of like in a coherent way until you take kind of like functional analysis or something like that, where that is then it's done in much detail. So, but I mean, in finite dimensions, it's just like a linear algebra where like the dot product plays a major role. That's basically all that it is. It's only in infinite dimensions that it really gets technical and complicated. But like until that, like you can kind of like most of the things you kind of like have seen many of the ideas. It's just like putting them in a more general framework. So, um, uh, um,
Okay. One last question. How do we know that the projection form is like the perfect projection? It's not like slightly bigger, it's slightly smaller.
Well, I mean, you can show, of course, it's an optimization problem, right? So you want to show that, you can kind of like do it like as a, like, like a, yeah, like, a Lagrange problem, right? Like it's like you want to minimize the distance, right? So there's like a distance function, and then we just show that this one is a minimum for like distance function, like but I mean, it's from the picture is very plausible. If you kind of want to do the picture and I mean, once you kind of convince yourself of this, like it's not it's too hard to hard to say that this would be the right formula. But yeah, it is possible to show it using calculus. But like which is kind of what least squares does as well. Like least squares is basically like a projection formula. It's just if you want to project kind of like you want to interpolate, but you can kind of like set it up as a linear algebra problem of like projecting a vector into the column space of a matrix, or like depends on how you set it up, but it's basically that. No. But yeah, but it's possible to show. Uh, Oh, the other thing I was going to say is that notice, if someone wants to notice it, that this is an SVD decomposition for the projection matrix, if it's not clear, because a projection matrix only has eigenvalues 1 or 0. So the singular values are also, ones or zeros. I'm just keeping the ones that are singular values 1. So this is already the SVD decomposition for any projection matrix. So like the projection matrices have like a super nice SVD decomposition. Right? So this is like the SVD decomposition. Or the spectral theorem, because they're symmetric. So more or less the SVD decomposition is the same as the spectral theorem with the matrix is symmetric.
It's very wonderful.
Yeah, exactly. So, right, because all the eigenvalues, the projection matrix only has two eigenvalues, 0 or 1, which are all non-negative. Okay, so there's no difference. This is the only difference that the similar values or the absolute value of the eigenvalues. that's not something you have to worry about here because, you know, the matrices as well. Um, okay, so the reason why I brought this projection maybe is because so why am I bringing this? It actually comes back to this thing that I was telling you a bit earlier. What with the probability stuff. So what I had said earlier, just to go back to the cubic case, what I was saying is that, well, you can write any vector, any qubit would be kind of like a linear combination. A linear combination of the spin up and the spin down vectors, which are now relabeled in 0 and 1 just to have like the same notation of quantum computing, right? But because the basis is orthonormal, right? Because the basis is orthonormal, right? If you take if you kind of like take the dot product, for example, with 0, with the 0 qubit. I'll just do it one more time just so that you see it more explicitly, right? Okay, so this one gives you 1 for what, because of what we were discussing, right? And this one would give you 0, right? Because like the vectors are orthogonal. And okay, so you can read off the coefficients right from the dot products, which we had already said, right? So you would find that C0 is this, and C1 would be this. Right? And then the probabilities are just the squares of this probability amplitudes, right? Which is their name. But then, and this is where I was saying that the direct notation sometimes take a life of its own. So if you look at the probabilities, what is P0? P0 would be C0 squared, right? C0 squared is just like C0 times C0, which is, that's kind of like obvious, right? So this is like 0V times 0V, right? Right. And these are just two numbers, right? These are just two numbers. So I can kind of like, it doesn't matter. Let's see where. Oh, right. The dot product is symmetric, right? So it doesn't matter if it's 0.b or b.0, right? You can put them in any order. So I'll just swap one of these two, right? But you see our friend, the projection here, right? Like this is our projection friend, right? This is like, this projection onto V, right? So you can write this as 0PB0. That everyone said it, likes it.
but the green tensor 0 is not 0.
Oh, no, right, because this is not the 0 vector, right? Like, this is just the you could call them the up and down if you prefer.
How do you represent the outer product between products?
Well,
Now the inner tensor, but
right, like the outer, I mean, I actually was going to talk about that next, but for example, when I talked about the composite system, right? But for example, like Alex has a qubit and Bob has a qubit just to follow their notation. I mean, there are two ways that they would usually write it. Like one way would be to just write it like this. Okay, just like one next followed by the other, or the other way to write it, which you would also see, is something like this.
So that's the outer product.
That doesn't wait. Well, right. By outer product, I mean it is just like the tensor product, right? Like the outer product and the tensor product of that. Or you unless you're thinking about something different from what I'm thinking by outer
Is
product.
the outer product like kind of like a cross product?
Oh no, like no, like that cross product is different because that's not associative, and also it only works for like vector with and remember this. Like it's the different like outer product. I mean, there's a thing called the wedge product, which is sometimes called sometimes I don't know if people call it also the outer product, but no, usually when you say outer product, you actually think about the tensor product. But that is not like I'll mention this in a moment, but yeah, like the way for them to kind of like write like a tensor product like of pants is like no one really writes it this way, so you either you write it like this or you could write it like this. So those are the two more common. Yeah.
I think you arrived at value for C1.
Oh, it's kind of like the same, well, is this one making sense like the value?
Yeah.
C1 is the same, you just kept it or bracketed with with one. Like you use the like you use the same equation as before, but you put like a one here. Yeah, and it kind of works in exactly the same way because the vectors are orthogonal, and then the only one that survives is now one with one. Okay, and
How are you allowed to like let 0 be 0 2?
oh, because remember, like this is where it's useful to think about what it means. This is like this is the dot product between the vectors. So it is doesn't matter in which order you take the dot product, right? U dot v or U dot v is the same as v dot u. But that's why I was saying that the notation kind of like takes life of its own, right? Because if you kind of like switch one of them, right, in their order, oh, then it's kind of like this one is sandwiched, is squeezed between the other two, right? And then and what's even crazier than that is that these like first actually I should kind of like put this kind of like in tensor notation, like just to kind of like have since we haven't drawn some pictures in a while. So if you wanted the tensor notation for this PV, right? In tensor pictures. So again PV was like this. So what you can do, what if you want to write again, a vector has one leg, right? Like that was the idea, like of well, I guess I could put it in well, I'll put it just V. Right, like a vector has a single leg, right? So this is supposed to be a matrix, has two legs, right? But they're built out of like the string vector. So you kind of like just put the legs facing opposite sides. Because if they were meeting one another, then they're being contracted, right? So you don't want to contract them, you want them to be free. But and so if you do it this way, then this is kind of like consistent with this because when you feed a vector to it, right? What is this quantity corresponds to in this tensor notation? It would correspond to, and again, this 0 is like a vector, right? Like it's a spin up vector. So so this one is kind of like being contracted from the right with this 0 vector, and the other one is being contracted from the left with that 0 vector. And then you can kind of like check that entry by entry does, I mean, that this number coincides with what you get if you do that. And then the other nice fun thing is that, I mean, this is where like the notation takes life of its own again. And then this is the same, right? This is the same as if you had written the diagram this way. Let's, I mean, it looks like silly, like, it looks, oh, you're not really doing much. It's kind of like a shift in perspective. And if you write it this way, you are thinking of it as being kind of like you have two matrices. You have two matrices, and you're contracting their indices. So that's kind of like the dot product in the matrices. So it's like the trace. We're not talking about that. Like, you can define like a dot product between matrices with the trace operation, like taking trace. So this actually is the same. All that I'm saying is that these things just happen to be the same as the trace. So this quantity, so the probability, this probability 0 is, which was this, coincides with the trace between kind of like the projection representatives for the vector v and the vector 0. So. I mean, it doesn't matter. The trace commutes, right? Like trace of A times V is the same as trace of B times A. So it doesn't matter. So the probability is kind of like the dot product between the projections representing each of the vectors. That's kind of what we do. It's kind of like another way to think about the trace between the think about the probability.
Zero in this situation.
Oh, P0, I should write it. You're right. Like P0 is like, P0 would be, the vector 0 is a vector, right? So you can do the projection associated to that vector. So P0 is just like the projection for that vector. So
So the only basis for the zero vector is inconsistent. So
well,
it's to add up all of the.
oh, no. But the thing is that there are two projections here at play, right? Like what I was saying is, like when you have any vector, maybe just let me go back to this picture that we had here. When you have a random vector, any vector in the world, you can find the projection onto the vector space generated by that vector, right? Which is always one dimensional. That's what that corresponds to. It doesn't matter what that vector is. So you can do it to the random vector that we're calling V, but you can apply the same idea to the vector 0 and to the vector 1. Yeah. So, and will you repeat? Oh, repeat that.
We're saying this is zero.
Oh, right. It will be symmetric. Yeah. But it's kind of like, okay, yes, although once you read, and yes, I guess you reverse the roles, but I wanted it to kind of like go to the trade formula because just kind of like show it from that perspective.
So
Mhm.
usually when we have some kind of symmetry matrix, right?
Mhm.
And we rearrange it while maintaining that symmetry,
Right.
we can sort of place our bets on some nice property that.
Yeah, and also like that. I mean, it's not that we never kind of gave some formal rules, but like the diagrams do have a lot of flexibility in, like, you can bend the wires and all that, so that's why I kind of like I'm playing a little bit with them, But yeah, like it's just kind of like we are arranging them in so that another formula, like another representation for the same formula, becomes more apparent. I think, and we have talked about that with the trace actually. Like the y is trace of A times V is the same as B trace of B times A, right? You know. right? Because if you had a matrix A, it has an index and an index, right? And if you had a matrix B, it has an index and an index. So the trace of A times B was like what you get just by contracting, right? So these were representing trace of A times B. But then what I had told you is like, imagine kind of like this being like a literal wire. If you just move the box around, right? Like you just end up like, flipping everything on its head. So you just end up finding, these. If you thought about this as a box that you can drag along the wire, of course, that's, it's just suggestive, right? Like it's not, I'm not, but you can kind of like turn it upside down, which is what people do in category theory and other things, where you just start like, let's just say that you have some diagrams or like a language, which with the following rules, and then you show that that kind of coincides with what the trace should be. Like there is like a way to formalize this so that it's a little bit more rigorous. Right now, I'm just kind of like doing it for playing around, like just suggesting formulas that we can always verify algebraically.
It's working. It must be like trying to take quote with.
It is, but there's like a way to do it so that it's really equivalent on the node. Like it is truly equivalent. But right now I'm just taking a more like pragmatic approach to it, where whenever I find it useful, I'll use it, but not taking it to like a like fundamentalist level that this is like the right way of like to provide it this way and
My last question was like, so for a tensor diagram, so we contract them to the method, but when there's a space in between each bubble, like all the top, like.
Oh, right. This was
Space like this.
well, no, in this case, like that's why I kind of like you know, like I wanted it right, like there's not much of like it's not okay, right? It's not super clear if I had just written this. Why would you think of this as a matrix rather than two copies of the same vector, if that's what you're asking me, right? So it has to be there has to be a convention that if you write it this way, you're thinking about it as in this matrix perspective, you know what I mean? Yeah. So there is kind of like an extra, it's not as it has to be like there's an ambiguity. I agree with what you're saying, and so we just let's agree, and that's why I use the same color and everything. So there's kind of to emphasize, I'm actually thinking of this as a single entity, right? Like, and that's why I'm putting it kind of like, yeah.
Just building on what you said, like if you go just one step behind, like.
Just give me a second to finish writing this, and I'll go back to the step behind. Okay.
Drawing the diagram for N0 PV bracket 0. We're just drawing the inner products between.
Right.
So we're literally like drawing that.
That's also
That also makes this the same way that this
Correct.
must be a tensor. This must be a matrix.
Right. Yeah, no, I agree. Yeah, there are many ways to kind of like reconstruct the same formula. Yeah.
And that is again the case or like just the diagram people thought.
Right. Okay, and then maybe because I always want to kind of like finish a bit earlier, just if there are any questions. So what I'll explain next time, what I'll do next time is and that's finally going to be the connection with the SVD, is that there are many fun things along the road to just get distracted of going on, but I think they're useful things also to discuss, like like this notation, like because it's like a very powerful notation. So next time, what I'll discuss is kind of like what people call like a bipartite state, which is kind of like this idea, like the way I'm presenting it, like you have two people, like usually like the literature they're called like Alice and Bob, right? Each has their own quantum system, each with a quantum system. And then the question is, what is the vector that describes like the composite, like the overall system? And that has to be a vector in the tensor product of the corresponding vector spaces. So the vector that describes like the system for Alice and Bob, vector for composite system, like the total system, composite system, is described by a vector in the tensor product of the vector spaces, of the individual vector spaces that Alice and Bob had, and the individual. And so that gets to the idea of like the entanglement, which is that if you have a vector in a tensor product, it's not always, it's always a sum of tensor products, but it's not necessarily a single factor, right? Correct, yeah. Exactly, right. And then there's like a refinement of the rank, well, not a refinement of the rank, but kind of like a continuous version of the rank, which is called like the von Neumann entropy. Which also measures. We're almost getting toward the end, but we can talk after. But then there's like this refinement of how entangled a system is, which is called the von Neumann entropy, which matches like the Shannon entropy. And after you can do like an SPV decomposition. So I'll maybe mention all of those. I'll talk about that next time. But I mean, this is like where like quantum mechanics has its spooky reputation for, because the entanglement is like it is a truly non-classical phenomenon, and it's kind of what makes it possible to play with it it can like do different things that you cannot just do with classical mechanics or classical probability. It does have like extra features which are really fun. But yeah, let's finish here because like the next thought, and that would be the last thing I promised about this quantum thing. And then like next week we'll do the SVD for the tensors. But like the example I want to do, so basically just to tell you the example I'll do after the SVD, we've talked about the SVD decomposition for the tensors, is I'm going to kind of like model binary sequences using a quantum system and kind of like give you like a training algorithm for like how there's this parity problem, which you may have heard of, like how do you like like if you have like a binary sequence whether let's say have like an odd number of ones, and how to train like like do like an learning algorithm to kind of like predict whether like a sequence like would be binary or not, like like the probability distribution of like the binary sequences. Well, I'll tell you more about that but the idea is to use kind of like these ideas of quantum mechanics to train the algorithm, and it's something that doesn't use gradient descent. So it's a different way of doing like training, which is kind of like fun. It will be, I think you'll like it, but I'm just giving you like a teaser. But let's finish here.